In this set of notes, we're going to see how to tell whether a reaction is associative or dissociative by looking at a set of thermodynamic and kinetic values. So let's start by looking at two different chromium complexes. You see we have a pentaamine complex here with one water ligand, and then the other one is just an aqua complex. We're going to look at how these exchange reactions of one of the waters, this one water or any of the waters in the aqua complex, how that ligand exchange rate varies as a function of the incoming ligand. So in this table we have a series of incoming ligands of different types, and we have the rate constants for those exchange reactions. So you see the fastest reaction for the pentaamine complex is 4.2 times 10 to the negative 4 per mole per second. And the slowest is 0.7. Okay, so that's a variation of a few units, 5 or so. Okay. Whereas for the chromium aqua complex, the fastest reaction and the slowest reaction are quite different, right? So this is about a factor of 2,000 times. And so you could say that the aqua complex is very sensitive to the nature of the incoming ligand, right? Whereas the pentaamine complex is not very sensitive. And so in terms of our mechanism, that must mean that in our aqua complex, that the reaction depends on the nature of the incoming ligand. And that's the feature of an associative, or maybe an interchange associative reaction, right? Because in those reactions, the first step is that the incoming ligand associates with the complex, and that causes it to be very sensitive to the nature of that bond. Whereas in the pentaamine complex, we have a case where it's not very sensitive. So in this case, it's not completely independent, right? There is some variance. So it's probably one of these interchange dissociative ID reactions. Okay. Here's another example of a reaction, an exchange reaction of, again, one water ligand, one aqua ligand on a cobalt complex now. Cobalt and chromium, you both might recall, are very slow exchange reactions, and so we see again a series of rate constants for that exchange that vary by a factor of 4 or so, 5 maybe. And this column here is how those rate constants vary compared to just water exchanging with itself. Okay, so for example, the azide ligand here exchanges at the same rate as water does. This one is 21% of the water exchange, etc. So again, we see a series where the rate constant does not vary by very much across this series of quite different ligands, and so we would assume that this reaction is dissociative. So there's a feature that we can use to quantitatively identify whether a reaction is dissociative or not, and that is by thinking about the rate determining step in a dissociation reaction, which is the breaking of a metal ligand bond, right? So if we start with a complex MO5X, where X is the leaving group, we have some incoming ligand Y, but we're not worried about what that is at all because it's not involved in that rate determining step, making this intermediate. And so what should be true in a reaction like this, since all we're doing is breaking a metal leaving group bond, right? Metal ligand bond, is that dissociation reaction should be dependent on that metal ligand bond strength, okay? And so if that's the case, then the rate constant K should be proportional to that bond strength, delta H bond. And this is not a linear relationship, but we'll see how this works. So we're going to start by thinking about the variables involved with kinetics. So this is the Arrhenius equation written in the natural log form. And you see that the natural log of the rate constant is equal to the natural log of this pre-exponential factor A minus the activation energy divided by RT, okay? And we're going to compare that to the thermodynamic equation, delta G equals delta H minus T delta S. But we have to get it in some form where we can compare the thermodynamic values to the kinetics values. So first we're going to think about the rate constant, how the equilibrium constant, how K, capital K, is related to delta G. So this is the equation. And so if you take the natural log of that equation, you get the natural log of K is equal to negative delta G over RT. And you can see that these are now starting to line up. So if we substitute in delta H minus T delta S into delta G, we end up with this equation. Okay, so this is that same equation. Natural log of the equilibrium constant is now equal to these values, negative delta H over RT plus delta S over R. Okay, so we have to make some assumptions now to compare these two, but we're basically going to be comparing the natural log of the equilibrium constant to the natural log of the rate constant. Yes, they're both K's. We're going to have to be careful with capital and lowercase letters here. So here is our assumptions. If this Arrhenius constant and delta S don't change very much as a function of the incoming ligands, that means those are constants, then we can kind of ignore these factors. Okay, so we could say that the natural log of the rate constant is proportional to negative EA over RT, and that the natural log of the equilibrium constant is proportional to negative delta H over RT, right? Okay, that must mean, and the other assumption here is that the activation energy for our reaction is proportional to the enthalpy change, and that's simply saying that that in that rate determining step we're breaking a bond in order to overcome our activation barrier. So if those are true, then the rate constant is directly related to the equilibrium constant. Or you could say the natural log of the rate constant is proportional to the natural log of the rate constant. So let's take a look at some data which shows this linear free energy relationship. So you can see on the x-axis we have our equilibrium constant, capital K, and on our y-axis we have the lowercase k, the rate constant, both written in the log form. So this is that relationship that we derived on that last slide. And what we have are, on this side of the x-axis, we have unfavorable reactions. Meaning that the complex that we start with is more favorable than the product. And on the other side, we have very favorable reactions, right? Okay. And on the y-axis, at the very bottom, we have very slow reactions. And on the top, we have very fast reactions. Okay, so let's think about what this means. And let's just start by looking at just the fluoride and the iodide, okay? So that linear free energy relationship is basically relating the activation energy to the enthalpy of the reaction, right? So when we say that a reaction is slow, it has a very large activation energy, right? And it has a very very large delta H for that bond that you're breaking, right? You have to break a strong bond. And so that's saying that fluoride is bound the most strongly to the metal, and therefore it's very difficult to initiate this reaction, right? And that's what we see. We see that the equilibrium favors the complex with the fluoride still bound, not the aqua complex, and that reaction is quite slow when it does occur. So the iodide is the opposite, right? So this iodide doesn't form particularly strong bonds to this hard acid cobalt. It's a pretty weak base as a base. And so therefore its equilibrium constant favors now the aqua complex, and the reaction is quite fast. So it has a low enthalpy of reaction, meaning that it's easy to dissociate. So in summary, if you have a linear free energy relationship, and this is not always true, right? If you do have a linear free energy relationship, it means that your equilibrium constant is directly tied to the strength of the metal ligand bond, meaning that that's your rate determining step.